Hello guys, welcome back. So today we'll be starting a very important concept which is called the outlier detection analysis. So let's understand what are outliers. So outliers are the values that look different from other values in the data, right? So they are can be either extreme values or they can be noisy values in our data, right? So we can see in the below plot that the red colored points are outlier points as they are different, as they are extremes, right? They are lying to the extremes, to either extremes of what the general trend of the data is. So this is the general trend. So the green points are showing the general trend. The red point, they are the extreme points or extreme uh, observations in the data. They are something called extreme observations. So it's important to study them, not only study, to know how to deal with them, right? Because they play a very important role when we are doing our feature analysis, when we are building a model. So what could be the reason? So errors during the data entry. So let's say we are preparing our data. Someone is preparing our data and they are preparing it manually, right? Preparing manually. In such cases, it's a very high chance that due to human error, there can be some kind of erroneous data popping up. Or let's say we are using some device to measure our data. Let's say, for example, thermometer in case of body temperatures, right? So if the thermometer is faulty, we might have some observations which can be extreme or which can be considered as outlier. Or they can be naturally occurring outlier data. So for example, if we look at the salary of a junior level employee versus a salary of a C level or a CXO level employee, that CXO level employee's salary can be considered as an outlier because most of the company's salary would not be even close to it, right? Sadly, would not be close to it. Now, the problems caused by the outliers. Outliers in the data, they can be very problematic during the model fitting, especially linear models, because linear models have an assumption of normal distribution. So they assume that the data is normally distributed. But if the data has many outliers, then the distribution would not look normal, right? Let's say salary, we are visualizing the salary of employees. So most of the employees' salary lies somewhat in this range. But when we consider the salaries of CXOs, they are here. So this would not be useful when we are trying to generalize our model, build a generic model, right? They may inflate the error metrics, right? Which gives higher weights to large errors. For example, mean squared error. So when we are trying to build our model, our goal of the model is to minimize the error. It is to minimize the error. But in case we are having outliers in our data, for example, again, the salary of CXO, since they are very much higher than what the average or the general salary is, they might cause the error to shoot up very high, causing inconsistencies in the model. Now, let's see how to deal about the outliers, how to deal with them, how to detect them, first of all, right? So outlier detection can be done very well using box plots. The box plot, as we know, is a visual method to identify outlier. And we have already discussed in the data visualization class that box plots can be very well used to plot the 25th percentile, 58th percentile of the median, or the 75th percentile, which is the Q3. Now, along with that, when we were looking at the plot, we also saw that there were two extreme lines, right? So this is Q1, this is Q3, this is Q2, which is the median. These are the extreme points. So these extreme points can be considered as a threshold point for the outliers. Any point lying to the right of this is an outlier point. Any point lying to the left of it can be also very well considered as outlier. How can we figure out this line? This line can be figured out by using this formula. So this line is Q3 plus 1.5 times Q3 minus Q1, which is also called the interquartile range. This is also called the interquartile range. And this line can be found out using this formula, which is Q1 minus 1.5 times the interquartile range, right? So this gives us a very good way to visualize our data, right? So this is the IQR method which we were talking about earlier. The lower bound can be found out using Q1 minus 1.5 times IQR. The upper bound can be found out by Q3 plus 1.5 times IQR. Now this is let's say we have placement exam marks out of 100. The most of the median marks looks to be 30. We have 30 as our median marks, and most of the marks are lying between 0 to 80. Now, or let's say this is 82. Now these marks are lying beyond 80, 82, which is greater than our upper bound, right? So what we can conclude that these are outlier points. So it's a very good way to visualize and visually see our outlier points. Let us look at a more sophisticated way to deal with it, which is called the isolation forest algorithm. It's a pretty advanced algorithm, and it's a tree-based algorithm that is very efficient and effective for both outlier and novelty detection in the high dimensional data. Now, when we have high dimensional data, it's very difficult to visualize as such. Just visually, we cannot figure out what the outlier can be. But this isolation forest algorithm, it's a very intuitive and a good way to sort of detect the outliers. What is the intuition behind it? So the sklearn documentation says that isolation forest isolates observations by randomly selecting a feature and then randomly selecting a split value between the maximum and minimum values of the selected feature. Again, let's go it again. Isolation forest isolates observations. So what it's doing? It's isolating observations by randomly selecting a feature. Let's say we have 10 features, we randomly select a feature, right? So let's say this was the distribution. Now what does isolation forest will do? It will create cuts in the graph. It will try to create more and more cuts in the graph. Now the points which we are not able to split, right? Which we are not able to split through, even with more and more cuts, they can be considered as outlier points, right? So the most important hyperparameter in the isolation forest is the contamination hyperparameter, right? So what does this contamination hyperparameter is, which we actually don't know. It's a hyperparameter, right? So it represents the proportion of outliers in the data set. Let's say we have a feeling that, okay, 1% outlier we would be having in our data set, right? So it's again just it could be due to domain knowledge, or maybe due to the past trends in the data. If we already know that we have some proportion of outliers present in our data, we could use this hyperparameter, and using this hyperparameter, the tree would try to split the data using the maximum and minimum values of the selected feature. Right. So now what is the limitation of this method? Because we exactly don't know the proportion of outliers. So we just have to play around with it, and maybe sometimes we would we would be short of detecting all outliers if we choose a low contamination value. If we choose a low contamination value. So it's always advisable to sort of go for 1 or 2 runs or more runs in the data set to again visually see if we can figure this out. Another advanced method is the elliptic envelope algorithm. The intuition behind this algorithm is again very simple. We draw an ellipse around the data points based on some criteria and classify any data point outside the ellipse as an in-layer or the green ones, and observation outside the ellipse is an outlier. Inlier and outlier points, right? So these are the outlier points, and these are the inlier points. So visually we can very well see using the elliptic envelope algorithm. So let's see and try to sort of implement these algorithms one by one in Python.